Can somebody confirm you can hear me?
We can hear you.
Great. Let's go down just a little. Right there. All right. Before I begin, are there any questions? Let me
With
see.
go ahead.
Go ahead.
With our unknowns responses, all of that communication will be through the unknowns notes. Correct?
Correct.
Thank you.
All right. Um, I did do some grading. I don't remember which lab it was, but maybe lab 6 has been graded, and I got that done very early Wednesday morning. So that the second grading will be turned in by this Saturday, and I think it's lab 6, but let me just take a look here. Hmm. Boy, see how slow my computer is because the the Zoom file is being made at the moment for the lecture, so I haven't finished that. So my computer is going to be working slowly. Yes, I got that finished, and so the that lab must be turned in by February 15th. So this Saturday, you must turn it in for the second grading. Any questions about lab 6 or any other lab or any other questions? All right, let's close that down. Oop, close that down. Should probably keep that open. Don't need this one though. Get that back up. All right. I don't remember if I mentioned today is February 13th, and we're supposed to be working on Lab 8, identification of gram-positive organisms. And you're also supposed to be working on your unknown project. I have not checked the unknown notes yet, but I did send out your first 3 results for 3 different tests on Tuesday, as well as I sent out your unknown number. So last Tuesday, very late or very early on Wednesday, I sent you those results. So you can begin work on your unknown project. And like I said, I'll look at that after the lab today. Any questions about what we're doing? All right, let's move on to lab 8. Lab 8, identification of gram-positive organisms. We're going to be talking about gram-positive cocci and gram-positive bacilli. The cocci will be Staphylococcus, Enterococcus, and Streptococcus. So all 3 of these different cocci family. And then there are 4 families of gram-positive bacilli we're going to talk about today. Listeria, Clostridium, Corynebacterium, and Bacillus. There are some video clips in today's lab, but anyone has any question about anything so far? All right, you're going to be using a dichotomous key today, as well as different case studies. You can find these last 2, the dichotomous key and the case studies, as separate files in Canvas underneath your lab module and lab worksheet. So I've got that right here under week 6 lab. There's lab module 8 for lab 8. And then there's the worksheet for lab 8. And there's the case studies for lab 8. There's the last case study. And there's the dichotomous key. Only use this dichotomous key for uh, Lab 8, do not use it for any other purpose, any other lab, especially for your unknown project, because it's designed specifically for Lab 8. On successful completion of this lab, you should be able to, one, understand the principles and how to interpret the results for these following tests: the CAMP test, the bile-sculen auger slant test, the SF broth test, and the optogen sensitivity test. And then you should also be able to use a dichotomous key to solve case studies involving gram-positive bacterial infections. When specimens are received in a microbiology lab for routine bacterial cultures, they are inoculated on culture media that will facilitate the growth of common pathogens and are placed in physical environments that will support their growth. Microbiologists use colony morphologies, meaning how the colonies look, and the gram stain to provide important information about the primary classification of the bacterial isolates. However, further biochemical testing is required to identify the species causing the patient suffering or any bacteria you're trying to identify. You need further biochemical testing. In this lab, we're going to talk about the CAMP test, the bile-sculen hydrolysis test, the SF broth test, and the optogen sensitivity test. CAMP is an acronym of the three microbiologist names who first described the amplified hemolytic effect of some beta hemolytic organisms have when they're physically grown very near Staphylococcus aureus. So CAMP stands for C. Christie, A for Atkins, and then MP for Munch-Peterson. You don't need to know these people, but you should know the CAMP test. What you do is you streak a beta hemolytic bacteria on a plate with a plate that has Staphylococcus aureus in one streak down the middle of the uh, blood agar plate, the bat plate. So perpendicular to the Staphylococcus aureus, you streak the test organism or the unknown organism that should have beta hemolysis, meaning in this CAMP test, everything has beta hemolysis. Blow this up really big, really, really big. So right there, you can see a streak of Staphylococcus aureus, and it's the dark color here. And around it, this is the beta hemolysis that Staphylococcus aureus is causing. Here is Streptococcus pyogenes streaked here, and the dark reddish color there. And then right there, this light section is the beta hemolysis that Streptococcus pyogenes shows. You'll note that there's no enhanced hemolysis of Streptococcus pyogenes near Staphylococcus aureus, so this is CAMP negative. No enhanced hemolysis in this region here. Any question about any of that? All right, here we have Listeria streaked here, and then Staphylococcus aureus streaked there. There's the beta hemolysis of Staphylococcus aureus. And right there, very thin, is the beta hemolysis of Listeria. And you'll note that Listeria has slightly enhanced hemolysis in this region near the Staphylococcus aureus. Further away, it only has the normal hemolysis, which is very slight. The beta hemolytic activity of Listeria. And you'll note that this enhanced hemolysis takes on the appearance of an arrow. Anyways, this is slightly positive enhanced hemolysis or slightly positive CAMP test. And then here we have this streak of Streptococcus agalactiae, and then the streak of Staphylococcus aureus. There's the streak of Staphylococcus aureus. Here's the beta hemolysis of Staphylococcus aureus. There's the streak of the strep right there. And you can see beta hemolysis around all of the streak. But right here, we have greatly enhanced hemolysis of Streptococcus agalactiae when it is grown near Staphylococcus aureus. And so this is considered CAMP positive, meaning greatly enhanced hemolysis. And you'll note the enhanced hemolysis has the appearance of an arrow. Any question about any of that? So normally the enhanced hemolysis takes on the appearance of an arrow. Let me shrink this down now. Up too far. Tried to stop it and it didn't stop fast enough. Any question about the CAMP test? Now remember, all the species tested are beta hemolytic, but we're looking for enhanced hemolysis near Staphylococcus aureus. The bioesculin hydrolysis test is a slant used to differentiate Enterococcus family from the Streptococcus family of bacteria. If the organism hydrolyzes esculin, it'll make the product esculatin. Esculatin is a dark brown or black precipitate that you'll see forming in the slant. So esculin makes glucose and esculatin, and then the esculatin is a dark brown or black color. Esculin negative is this, where the tube remains its normal color, whatever color that is, sort of a light brown color. And then esculin hydrolysis positive has a darkening in the tube, about 50% or more of the tube. If it's only a slight speck or a dash of darkening, that is considered negative, by the way. So you do want the black to be around 50% of the tube, or the dark brown to be 50% of the tube, before you consider it esculin positive, bioesculin positive. Any question about that? So negative will be all of the members of the family Streptococcus. They cannot hydrolyze bioesculin. And then what will be positive will be members of the Enterococcus family. Will be bioesculin positive. All right. The next test we're going to talk about is the SF broth test. SF is an acronym for Streptococcus faecalis. Streptococcus faecalis is what we used to call the old name for Enterococcus faecalis. So we no longer call it Streptococcus faecalis, but in the old days, before obviously the DNA synthesized the bacteria, they thought that Enterococcus faecalis was in the same family as Streptococcus, and so they called it Streptococcus faecalis. And one way to separate out Streptococcus faecalis from the other members of the Streptococcus family were to do the SF broth test. Now remember, there is no species Streptococcus faecalis anymore. That's the old name. It's currently Enterococcus faecalis, which is in another family from Streptococcus. But if you have a SF broth and then you grow the bacteria in the tube normally is purple. and that's a negative growth in the tube, meaning no fermentation of the sugar glucose. In the normal color, it starts as purple, and if it's negative, it remains purple. But if the bacteria can ferment the sugar glucose, it'll make acid products, and that will change the SF broth tube from purple to yellow. So this is FF broth positive, and Enterococcus faecalis is SF broth positive. All the members of the Streptococcus family are SF broth negative. Any question about the SF broth test? All right. The important thing to remember about this test is that it can separate out Enterococcus faecalis from the other members, not other members, the family of members of Streptococcus family. And it's a little complex what the naming is, but we still call the test after the old name of Enterococcus faecalis, which was Streptococcus faecalis, and that's why we call it the SF broth test. Any question about any of that? All right, let's move on to the optogen sensitivity test. The optogen sensitivity test is a test used to differentiate Streptococcus pneumoniae from other alpha hemolytic Streptococcus. So if you have a species which belongs to the Streptococcus family and it gives alpha hemolysis, let me show you that. See if that's good enough. Well, let's go a little longer. So here we have our colonies, the off-white or whitish color of the colony, and there's darkening around each of them. That means that's alpha hemolysis. And if we know that this is a member of the Streptococcus family and has alpha hemolysis, we can then run the optogen sensitivity test where we streak the bacteria here in this region of the plate and then put down a disc containing the antibiotic optogen on the bacteria, then incubate the plate, and then take a look at the growth on the plate. If the bacteria, which is Streptococcus and alpha hemolytic, shows resistance to optogen, meaning there is no zone of inhibition as shown here, or the zone of inhibition is less than 14 millimeters inside, then we say the bacteria is optogen resistant, and it is an alpha hemolytic Streptococcus, but it is not Streptococcus pneumonia or pneumoniae. Okay? If, on the other hand, the zone of inhibition is 14 millimeters or greater, it is optogen sensitive, and it is Streptococcus pneumoniae. Any questions about how you run the the optogen test, testing for Streptococcus pneumoniae, separating it from all other forms of alpha hemolytic streptococci or streptococcus? All right. So those are the biochemical tests we looked at today. You also need to utilize a dichotomous key that describes the tests that can be, and then use the dichotomous key using dichotomous logic to isolate what your bacteria is. For example, if we have all bacteria and then we run the gram stain, you can separate the bacteria into two groups, the gram-positive bacteria and the gram-negative bacteria. We then scratch out the gram-negative because it's gram-positive, and then you can run another test after doing the gram test. And what you can do is look at the cells to see their cellular morphology. Are they gram-positive bacillus or are they gram-positive cocci? If they're cocci, then we can then cross out gram-positive bacillus. And then with the gram-positive cocci, we can run another test, such as the catalase test, to separate the gram-positive cocci into those which are catalase positive and those which are catalase negative. If they're catalase positive, then they are belonging to the family Staphylococcus, and if they're catalase negative, they belong to the family Streptococcus or Enterococcus. So we're going to cross out the catalase negative and then proceed with the catalase positive, which are Staphylococcus. You can then run the coagulase test, and if it's coagulase positive, it's Staphylococcus aureus. If it's coagulase negative, it is a Staphylococcus, but it is some other Staphylococcus species other than Staphylococcus aureus. So we're going to cross out the coagulase positive and then follow the coagulase negative. And then we can do the novobiocin test. Let me blow this up so I can read it a little easier. And if they're novobiocin positive, the Staphylococcus is Staphylococcus epidermidis. And if they're novobiocin negative, the Staphylococcus is Staphylococcus saprophyticus. Any question about really dichotomous keys and dichotomous logic? That's it for the lab module. We'll go to the worksheet in just a minute. You're not physically going to be performing any of these activities because everything we do is online. However, you will be held responsible for knowing how to perform and interpret these tests. So view the following video clips. We have one showing you both the SF broth test and the bile esculin test. And then we have another video showing you the camp test. So view those videos. Then let me go to the worksheet. And then go to the worksheet for question 2 or point 2. Review how to interpret the following test and completing the chart you'll need to refer to some previous labs as well as this lab. So for the gram stain, the results have already been put in for you. But if you have a positive result, the gram stain will be purple. And if you have a negative result for the gram stain, the result will be pink. For the Schaefer-Fulton stain for endospores, put in the color you see for a positive result and the color you see for a negative result. For the negative stain for capsules, put in the description of a positive result. And if you need more room, just expand the cell in the table and then put in the results that are negative for the negative stain for the capsules. So remember, a negative stain is a stain for viewing a capsule, which is a secretion around the cell that you can actually see under the light microscope. Not light microscope, see under the light microscope. Did I say that right? I might have. And you need to give a description. A one-word answer will not work. You might be able to do it in like 3 or 4 words. And then give the positive result for the catalase test, and then the negative result for the catalase test. Give the positive result for the coagulase test and give a negative result for the coagulase test. Both of these, as well as this one also, you can actually discuss using one word. It's possible. Just have to figure out which one word. But if you have a sentence discussion, that's fine. And if you need more room, you can write over here. And if you really need more room, you can write at the end of the table as well. You just need to explain where it goes to. Um, and then give the positive result for the oxidase test, just give the color, and then give the negative result for the oxidase test. Once again, you can give the color. For the CAMP test, give the positive result, and this, you really need 3 words to discuss it. Something like enhanced beta hemolysis, which is actually closer to 4 words, and then the negative result. I guess you could say something like an arrow is seen, no arrow. Give the positive result for the bile esculin hydrolysis. There you can give the color, and then you can give the color for the negative result. For the SF broth test, give the positive result. Once again, you can give the color, and for the negative, you can give the color. For the optogen sensitivity test, for a positive result, you have to give the size of the zone of inhibition is greater than a certain size, and then the negative result, something similar. And for the basotracin sensitivity test, once again, for the positive result, you have to give that the size of the zone of inhibition is greater than a certain size, and then the same for the negative result. So these two may need a little description. All right. For 3A, we have a video for you to watch to develop and use a dichotomous key. You do not need to construct a key for this class. However, the video will help you understand the general idea of making and using such a key, which you kind of have to do for your unknown project. If you're perfectly comfortable with using and understanding a dichotomous key, you don't even have to view this video. But if you want practice or you need practice, then view the video and go through the example. And then 3B, we have a dichotomous key and all of these species which will be used and discussed in the dichotomous key. And you're going to need the dichotomous key to answer the case studies. Put your answers for case study 1 here, your answer for case study 2 here, your answer for case study 3 here, etc. So put your answers for the case studies here. You can find the case studies. Well, let me show you where they are, first of all, in the lab. They're underneath the lab module 8 and underneath the worksheet for lab 8. And I'm sorry, they're all together as a separate link. That's the way the person who made them sent them out. And I decided to keep them this way because if he changes one of them, I'll only need to change this. I won't need to change a whole page full of all of them put together in one page, which actually has happened. He did change, I think it was case study 4 or case study 5. And so I had to change that. And I just actually put the new case study 5 up and then put either a new link to it, unless the link was actually going to it and whatever. So I decided to keep it this way where you have to work on the links. But here are the case studies here, 1 to 8. Let me go through the first one and I'll show you the second, but you guys can spend your time on the case studies. I've got it here someplace. There it is. Case study 1. I'm showing it here because it'll view better. Let's get rid of that. Case study 1 is a 13-year-old teenager attended a week-long summer scout camp. Upon returning home, his mother noticed a pustule beginning to develop in a spider bite on his arm. The area is warm to the touch and is becoming extremely tender and painful. When her son starts running a fever, she takes him to a walk-in medical clinic for evaluation. The physician orders a gram stain of the exudate and a routine culture. And here are the findings. Here is the gram stain. Come on, I gotta blow this up. Right, there it is. So this is the gram stain. That's hard to see there. So let's go up here. These big red things are actually the boy's cells. And these are the bacteria causing the infection in the boy. And you can make out pretty much the shape and obviously the gram stain from this. You can actually even determine the growth arrangement from this. Let me shrink this down now. Yeah, about there is good. And there's the blood agar plate with the bacteria isolated from his wound growing in the blood agar, which you can see the bacteria here and the hemolytic pattern. Shrink this down a little more. And then they took the bacteria here and did the catalase test, was putting hydrogen peroxide on the cells. And there's the results of the catalase test. They then did the coagulase test, putting the cells in rabbit plasma, and there's the result of the coagulase test. And then there's one further test, which isn't discussed in this lab, but you can find it in the tests for your unknown project. They grew the bacteria on mannitol salt agar plate. And this is the normal color of the mannitol salt agar, and this is the color of the mannitol salt agar plate after they grew the bacteria on it. And if it grows on mannitol salt agar, it means something, as well as the fact that if it is this color, it means something. And that helps you identify the species of bacteria. Like I said, if you need to look up what the mannitol salt agar is trying to tell you, you can look up in the unknown project, which I probably could show you. Here, so you have to look at mannitol salt agar in a previous lab. I'll try and make a link here so that I can put that in there, but it's not there at the moment. Funny, I didn't notice that in the earlier lab. I must have not checked. Where do I have that? Right here. And then answer what bacteria was isolated and put your answer in the worksheet for case study 1. For case study 2, you should note the test 2 is the basic trace and sensitivity test. Let's go to case study 2. Case study 2 is a 27-year-old female receiving prenatal care. At the end of her last trimester, she went into her OB-GYN physician, and the OB-GYN just did a routine vaginal culture. The woman is not exhibiting any signs or symptoms of infection, but when they got the bacteria from the culture and then they cultivated on blood agar plate, you can see the hemolytic pattern of the bacteria here, and that troubled them. So then they did a gram stain. You got to blow that up once again to see what that is. I can actually see what it is, but you can do that. You can tell the color for the gram stain, but to see the shape, you might need to blow it up. Come on, let's go to the next test. They then did the coagulase test, excuse me, the catalase test, and there are the results there. They then did the basotracin sensitivity test right there. And remember that's stated in the worksheet what that test tube is right there. Basotracin sensitivity test. And whoop, where am I? Here we go. And then they took this bacteria and did the CAMP test. And there's the results of the CAMP test. So that's further results. And then answer what bacteria was isolated. Any questions about doing the case studies or anything about lab 8? All right, if not, I will be here until 8 o'clock or the last student logs out to help you with this lab and answer any questions. I'll go ahead and get started on the lab. But remember, if you have a question, I will be here only until the last student logs out, and then I'll log out as well.